2017 higher paper for year 10, but this is the double award paper as well because it's a unit 3. So this was in 2017. It's up to 60 marks. Question 2 is going to be, page 2 is going to be the equations that we might refer to later on. And we'll jump straight into question 1. Question 1 is about using washing machine and saving energy and the efficiency of the washing machines. There's a few quotes in there and there's some numbers, but I'm going to go straight to the question and read the question first of all, because I may not need any of this information at the top at all. So let's go to the question. Use equations on page 2 to calculate the cost of the washing machine at 40 degrees Celsius if 1 unit costs 16 pence. So the question is, how many units have I used? And on page 2, it gives us the equation. Units 2 is the power times the time. But the power is always going to be in kilowatts and the time will be in hours because we're looking for the units. It's just the units here that we use for power and time. So 40 degrees is what we're interested in. 500 watts. So that's 0.5 kilowatts times the time, 90 minutes. 90 minutes is 1.5 hours. So if I put that into a calculator, I get that many units. That's what I've got to pay for. And they come at 16 pence each. So I've got to pay for that many at 16 pence each, which is 12 pence. The Energy Saving Trust suggests that the washing machine clothes are washed at 30 and that will reduce your energy by at least 40%. So that's 40% off. Use the data to investigate the claim. So we're going to do exactly the same up here as we did here. This was at 40 degrees. So if we're going to save 40% of that, 40% of that would be we would save 0.3 units. That's 40%. So if we're going to save 0.3 units, our new amount is that much. So if we save, if the new one cost uses that much energy at 30 degrees, if it uses this much, then we have saved 40%. So let's work that out. So we're going to do the same as up the top. The units used is the power times the time. The power is still 500, but the time is now 1 hour. So that's 0.5 kilowatts times 1 hour. If you wash your clothes at 30 degrees, then you'd have used 0.5 units. Well, in order to save 40%, it has to be this. So it's less than 40%. It's going to cost more energy than this. So it's not 40%. It's less. Bit complicated, that one. Bit fiddly. Washing the clothes at 30 degrees saves money on household bills. Why does it also help the environment? So what's electricity got to do with the environment? It would reduce the amount of carbon dioxide produced. To burning fossil fuels. And why is that good for the environment? So less impact on global warming. We're linking carbon dioxide and global warming. The machine is connected to a ring main. The voltage on the ring main is 230. lots of wires. Which wire is the fuse connected to? The fuse should always be connected to the live wire. Describe the function of the live wire. So this is knowledge base, straight out of your book. If the metal wire touches, if the live wire, I'll say, all the wires are going to be metal. If the live wire touches the metal case, the earth wire provides a low resistance path for the current to travel, protecting the user from electrocution. Straight out of your book definition. When the voltage is 230, the power of the washing machine is 500 watts. However, it needs to be able to cope with 2,400 watts. So what fuse do we need? Well, we need to know what current is running through this appliance, and then we can work out what fuse it needs. So it's all about working out the current. I'll go to page 2. I'm going to use this equation here to find out the current, because it's to do with the power and the voltage, which is also in the question, but I got to rearrange it. So I'll start by just writing that equation out. Power is voltage times current. That's what it said on page 2, but I want to find the current, so I'm going to do it that way. Now the power needs to be able to handle that much power, and the voltage is 230 volts, which means at the most, if it's running at maximum power, it will be a current of 10.4 amps. Now the question said that this person has chose to put a 3 amp fuse in. As soon as you put a 3 amp fuse in, 10.4 amps starts to flow, fuse breaks straight away. So a 3 amp fuse is not suitable, as it will blow straight away. A 13 amp fuse is better. It's given us a choice of 3 and I'm choosing 13. And that's a big question 1. Question 2. We have a graph of a wave. I can see that there's 2 waves here. We've got this first wave up to this point, and then we've got the second wave here. So there's 2 waves. We have a wavelength, which is signified here by this letter X. And I've remembered that there's also an amplitude, which goes from the middle to the top. Let's have a look what the questions are. Use the information to calculate distance x. So from here to here, that's also the same as from here to here. That's the same distance. It's one wave. And if the whole thing is 3.2, this is halfway. So from here to here must be 1.6. So that's the wavelength also. It hasn't said it yet, but I know that that's the wavelength. A wave takes 5 seconds to travel 40 centimeters. Use an equation for page 2 to calculate the frequency of the wave. And it's for 4 marks. So this is telling me I'm going to need to use 2 equations to do this. Now the first equation I'm going to do to find frequency is, well, let me show you which one it is. We're going to use these 2. I'm going to use this one first. Wave speed is frequency times wavelength, but I want the frequency. So the frequency is the speed divided by the wavelength. That's what I'm going to use. Well, I got the wavelength from the previous question, but I won't have the speed. but I can work it out using this one. So that's what I'm going to do. Let's delete that. So I said the speed is the frequency times the wavelength. The question wants me to find the frequency, so I need to change the subject. To find frequency, I'm going to do speed divided by wavelength. I know the wavelength because it's here, 1.6. But I don't know the speed. It doesn't say the speed anywhere. But I do have this information here, which will help me work out the speed. Speed is distance divided by time. The distance is 40 centimeters and the time is 5 seconds. So that's a speed of 8. And then I'll take this number and put it back over here. So now I've got 8 meters per second as my speed. Divided it by the wavelength. 8 divided by 1.6 gives me an answer of 5. It has a frequency of 5. Don't forget, if you see a question like this with 4 marks, you're going to have to do a similar sort of thing. You use one equation, then you're going to find another equation to bring the answer back in. Wavefronts travel towards the barrier. Complete the diagram. So the wavefront diagram looks like this. These are just like the tops. These are the peaks of the wave, and the distance between them here, that's a wavelength. But the wave is actually going in that direction, down with a ruler. So can I use it? Oh no, that's worse. So it's going to go up with a ruler to there. Then when it hits here, it's going to reflect off. Now remember, to do a reflection, we need normal, and this angle is going to be the same as the reflection angle. So I'm going to try and draw it as similar as I can. They're about the same angle. But I haven't drawn the wavefronts. I've drawn the direction of the wave. The question says, show the path of the wavefronts. And the wavefronts are just the tops of the waves. So we've got 1, 2, 3. There's another one. There's another one. There's another one. There's another one. The wavelengths aren't going to change here. It's just reflection. Refraction would change the wavelength, but reflection doesn't. So I'm going to have them all the same wavelength, same distance apart. I'm going to try anyway. Next question. A student investigates current voltage characteristics of a lamp. So we need to draw a circuit diagram. This circuit diagram, this comes up a lot as well. We need a power supply. We need a lamp because we're going to test the lamp. We need a way of measuring the voltage on the lamp, which is a voltmeter in parallel. We need a way of getting the current. So we're going to put an ammeter in there. And we also need a way of changing the voltage. And the best way to do that is to use a variable resistor. And that will be the circuit. The only thing here that will change is sometimes they may say of a resistor, in which case you draw the resistor there. Or a diode, and the diode is that symbol. And that can replace the filament bulb. But as this question says filament bulb, I'll put a filament bulb there. So the student collects these results. I think we're going to plot a graph. Plot the data and draw a suitable line. So current is going to go on the y-axis. Voltage is going to go on the x-axis. And we're going to want these points here. Let's just have a look. So the biggest voltage we've got is 12. The biggest current we've got is 1.10. So what would be a good scale here? Let's do the voltage one first. The biggest voltage we had is 12. So I think I'm going to go 2, 4, 6, 8, 10, 12. The biggest current we have is 1.10. So I think I'm going to go 0.2, 0.4, 0.6, 0.8, 1, and that would be 1.2. So here, this line here, that's going to be my maximum point. And then we just plot the graph, plot the points. So our first point was 0, 0. The next one is 2 volts and 0.4. You should have done this by now. 4, 0.76. 76. So look what 76 is. That would be 0.7 here. Each little square is worth 2. So that's 72, 74, 76 is here. That's 76. So let's come along here. Each little square is with 0.02. So 4 and 0.76. 6 and 0.94. Same scale. 10 and 1.08. And 12 is 1.10. Now that's not a straight line, is it? But it's good. I didn't expect a straight line. I expected a curve, because filament lamps give us a curve. Filament lamps will always give us a curve. Resistors will give us a straight line. Filament lamps give us a curve. So she concludes that the resistance of the lamp decreases as the voltage increases. Explain using calculations whether you agree or disagree. So we need to look at the resistance. Resistance is voltage divided by the current. That's on page 2. So let's do some for different voltages and we'll see. So let's do any ones. Let's do 4 volts and let's do 12 volts then. So at 4 volts, we're going to use this equation. I've got 4 volts divided by the current at 4 volts is 0.76. That will give me a resistance of 5.3 ohms. But if I do 12 volts, the current was 1.10. So 12 divided by 1.10 equals 10.9. As the voltage has increased, so the voltage is getting bigger, what's happening to the resistance? The resistance is getting, it's not 10.9 volts, it's 10.9 ohms. As the voltage is getting bigger from 4 to 12, what's happened to the resistance? The resistance is getting bigger. This person said it gets smaller. So they're wrong. Wrong. I disagree. The resistance is getting bigger. It's increasing. That's question 3. Question 4. We've got a heat equation, a heat question. Explain why the aluminium loses heat at a faster transfer. So it's something to do with aluminium, and we've got to mention why it's faster than plastic. So this is a conduction question, okay? So we're talking about the frame. Let's have a think then. How will I answer this? We've got aluminium is a metal. Which is a good conductor. UPVC is plastic, which is a poor conductor. Metals let heat pass through quicker. This is what the whole question's about, because because metals have 3 electrons which collide with the atoms in the lattice, passing on heat energy, making them vibrate more vigorously. Plastic or other insulators don't have 3 electrons, so the heat transfer is slower, and that pretty much answers the question. So this is an uninsulated loft. Explain how heat is lost to the house when it's not insulated. Refer to the ceiling, the loft space, and the roof tiles. So how does heat get through the ceiling? Well, the ceiling is a solid, so that must be conduction. The loft space, that's the air inside the loft, so that's a gas, which means we're going to have convection currents. And then how does it get through the roof tiles? Well, the roof tiles are solid again, so there'll be conduction, but they're probably black as well, which means they're going to absorb and emit the radiation. Why does reducing energy losses from our home benefit the environment? Yeah, we don't have to produce more heat, which has less impact on global warming. Because to make heat, we might have to burn fossil fuels. So it's exactly the same answer, or very, very, very similar. Question 5. So we have the order of the waves. I always like to draw a big wave here and a smaller wave going down to gamma. Just helps me. I can see I have to put these in order now. So basically I'm looking for the numbers that go here, 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 and here. I'm going to do the frequency ones first, I think. They're going to be easier because I've got the smallest and the largest. So here is going to be anything, the frequency, this has got the high frequency. Sorry, no, that's a low frequency, and this is the high frequency. So anything lower than this number goes in here, which means it's that one. That one's going to go here because it's all the big high frequencies. Numbers bigger than this, you get here because we increase in. That leaves me with these two to go in the right order here. And I'm not looking too much about what they mean. I'm just looking at some patterns. So this number here, 1 times 10 to the minus 3, that's going to be 0.003. I'm looking for where that finishes on another one, which is here. So this is going to go here. And that means this one's going to go here, which makes sense because I've got this number here matching up with this number here to carry on the pattern. Looks really complicated, but with a little bit of thinking, you can work it out. All EM waves transfer energy. The shortest waves are the most ionizing. The table below shows the energy values in incorrect order. So all of these are in the incorrect order. Rearrange them, so we have to write them in order of energy values. This one's got the most energy. It's got the highest frequency. this one's got the least. So it's putting the numbers in order. So the smallest number there, the minuses are going to be tricky. The smallest number there is going to be anything less than 2 times 10 to the minus 24. The biggest number is going to be that one. So then again, just like we did earlier, we'll put these in order, which means where do they carry off? This one's going to go here. This one's going to go here. And that one will go there. Question 6. How does this supply a reliable supply of energy as efficiently as possible? So it's all about the national grid. First of all, so the order that's going to happen is we've got the power station. It's going to go to a step-up transformer. And what that's going to do is it's going to increase the voltage, decrease the current, so the wires don't get as hot, and they don't lose as much heat energy. If you're not wasting energy, that means it makes it more efficient, because you're wasting less energy. After the step-up transformer, the electricity goes to a series of pylons and high transmission wires before it gets sent to a step-down transformer, which does the opposite. So that's going to decrease the voltage, so it's safer for homes and consumers, which is where it's going to go next. After the step-down transformer, it goes into homes. Here is a table about the national grid demand. The national grid demand here is in megawatts and the time of the day. I can see a peak here. I can see the lowest point here. Winter is higher than summer, probably because it needs more, you in the house more, you need more electricity, more heating. But the pattern is roughly the same. It's just higher up for winter. We've got lots of numbers here. I'm not even going to look at them yet. I may look at them in a bit to see whether I need them. Use information from page 2 and an equation from page 2 and this information to calculate the percentage efficiency. So if you go to page 2, you find efficiency equals the useful output divided by the total input times by 100. So I'm just going to look for those numbers. I'll go back to the numbers and have a look. Right. Maximum demand, output capacity, length of wire, heating in cables. Which of these is the useful output? So the useful output is going to be this one. That's how much it's going to be making. So I'm going to put 63 gigawatts there. But the input's tricky, because if the national grid is giving out 63 gigawatts, but it's wasted that much, so that input, how much went into it, is going to be a combination of these two, and then you've got the megawatts combined with the gigawatts, so that's got to be the same. So awkward. Right, so 63 gigawatts, if I'm going to change it to megawatts, it's going to be 63,000 megawatts. Now I can add them, so I've got 63,000 megawatts added to 1,420 megawatts. So the total that went into the national grid must have been 64420 megawatts. And so that's going to come down here. 64,420 megawatts. Oh look, this is gigawatts now and megawatts there. So I'm going to turn that into gigawatts as well. I'm going to get rid of that gigawatts. And I'll turn it into megawatts. Which means I've got this calculation. And don't forget to times it by 100. Which gives me 97.8%. That is very hard. And yeah, very, very difficult. Which leads us on to the next question. So we want the mean power used in gigawatts. Hopefully this will be easier. So the mean power used in gigawatts. Oh, here we are. This number here, look, is actually used. Oh, that's terawatts. So 360 terawatt hours. A tera to a gig, I'm going to change that over. So that's 60 gigawatts. Divided by the time, we want the time in hours. 8766. And if we divide those numbers, we get 41.1. This is hard. Last question. So maximum demand, so we're just going to go through all the data and look at which one it is, and the answers are 1 and 3. And if you're not sure, let me know. Yeah, ask me, but those are the answers. Right, that was tricky. Just to remind you, 28 out of 60 on this paper was an A grade. You needed 36 out of 60 for an A star. 20 out of 60 got you a B, and only 13 out of 60 was enough for a C. That last question was really hard. Don't beat yourself up too much about it. Bye.